The next thing I want to do is find how do we determine local minimum and local maximums. So I already entered this function into my calculator, and I'm going to go zoom 6 and see what the graph looks like. Well, this graph has a lot of turning points. As I see it, it has a turning point. Well, it doesn't show up on the smartboard, I don't think. But I'll have a turning point there. I'll have a turning point there. Looks like I have one there. Looks like I have one there. It looks like I have at least 4 turning points. When I'm trying to find a local maximum or a local minimum, I need to identify the interval. I need to identify the x values that I'm looking at. So, first of all, on this here, most of my activity is happening between -4 and +4. So I want to make this a little bit easier to read. So I'm going to change my window, and I'm going to change my x minimum to -4, and I'm going to change my x maximum to +4. And now I'm going to push graph. Yes, and I can see that that's where the activity is happening. So I can also see that the end behavior conforms to what I expected from my determination of end behavior. I have a down-up type of end behavior, which is consistent with the leading coefficient being odd and with the highest power being odd and the leading coefficient being positive, just like x cubed. So I see that I have at least 2 local maximums. So my graph, I can't write on the calculator, so I'll try and make it look like this over here. But my graph looks something like this. And so I want to start off by identifying there's a local maximum right there, and there's a local maximum right there. So let's identify those 2 local maximums. I'm going to go second, calc, and I want to find maximum, which is 4. Okay. I need a left bound and a right bound. What are they asking me for? They're saying if here's my local maximum right here, in the blue where I drew it just a second ago, right here's my local maximum. I need to find a left bound and a right bound of x's. So I need to go to that side for the left bound of that dot and this side for the right bound of that dot in order to find this local maximum. If I make a mistake and I go too far to my right, if I go make my right bound way over here, that is going to include 2 local maximums. And I'm asking it for a maximum. It's going to give me the highest one of those 2. I want a local maximum. I want a turning point. I want the spot where on either side of the hump, it's going to be higher than anything to that side and anything to that side. That is my local maximum right there. So I'm going to say my left bound, I would like my left bound to be, well, somewhere to the left of what looks like about 2. So I'm going to -2. So I'm going to say my left bound is -3. And I hit enter. And I can see that I want my right bound. I certainly don't want it too far over to the right, but it looks like I don't have another maximum between 1 and 1.5. So I'll call my -1 and -1.5. So I'll call my right bound -1.5. And I push enter. Now it's asking me for a guess, but you'll notice those 2 little arrows that are up at the top. One's kind of pointing that way, and the other one is pointing kind of that way. That is showing me the interval on the x-axis. If I follow those down to the x-axis, that is showing me the interval that I'm looking for my maximum. And that's about right. That only includes 1 local maximum. It doesn't include multiple local maximums. I don't want to make a guess. I push enter. And sure enough, it's blinking right there at just the spot that I thought. So I have 1 local maximum. I have a local maximum of y equals, well, that is a 8.8 e to the negative 12th. So this is a calculator issue. Whenever I see a big e to the negative 12 or big e to the negative number, I know it's really telling me that it's 0. So I have a local maximum of y equals 0 at x is equal to 2. Again, there's a calculator, a little bit of a rounding thing. X equals negative 2. So I can write it like that, a local maximum of y equals 0 and x equals 2, or I could just put the point in. I could say that is at the point negative 2, 0. That is one local maximum. Well, I see that there's another local maximum over to the right, so I have to do it again. Second, calc. Maximum is 4. Well, I can see that the next dot, which is this one right here, corresponding to that one right there, is my left bound. If I chose 0 as my left bound, that would be okay. So I'll choose 0. And I'll choose as my right bound. Well, I'll choose 1. That should be okay too. 1 as my right bound. So that's the interval that I'm looking at. I don't want to make a guess. I push enter. And it's telling me I have a maximum, another local maximum, of y equals 0.8294, which I would round off to 0.83. At x is equal to, I might round that off to 0.40. And as far as I can see, those are my only two local maximums. Well, if I want to find my local minimums, I have to do a similar kind of a thing. If I'm looking at my my representation of the graph on the calculator, I can see that I have one local minimum there and another local minimum there. Now remember, this going down forever is an ultimate minimum of negative infinity. But I'm not looking for the ultimate minimum. I'm looking for the local minimums that are between two distinct intervals, and that where I have a hump, where I have a turning point. So I'm going to calculate my first local minimum. I'll go second, calc, and I'm going to go minimum for number. I'm going to hit number 3. Well, my left bound is way over to the right there. So I want to move my left bound back over to the left because I'm going to find them from left to right. And I can see that about negative 1.5 will be to the left of my local minimum. Yep. And I'd say negative 0.5 would be to the right. Negative 0.5 would be to the right of my local minimum. Yep, I can see my intervals. My two arrows are kind of up at the top. They're identifying a nice interval where there's only one local minimum. I don't want to make a guess. I push enter, and I find that I have a local minimum, local min of y equals negative 4 at x equals negative 1. That's my first local minimum. I want to find my second local minimum. I'm going to go second, calc, go minimum, and I see it looks like it's right around 1. I'm not positive it's exactly 1, and rather than take a guess, I'm going to say, so I'll have my left bound. I don't want to start my left bound at my other local minimum. I want to move it over a little bit. So I just tap over. I don't have to give it a number. Now I'm clearly on the up part of the graph that's going to hit that local minimum. Better yet, I'm going to do it closer to the interval. It would work from here, but I'm going to do it at, let's say, I'm going to do my left bound at 0.5. That's my left bound. And I'm going to make my right bound at 2. So I'm going to go my right bound at 2. So I can see my interval definitely covers my local minimum there. I don't want to make a guess. So I have a local minimum, another local minimum of y equals 4.5 e to the negative 12. So I'm going to assume since e to the negative 12 is a really, really tiny number, I'm going to say that is 0 at x equals 1. You can see the calculator poses some problems. It doesn't give us exact numbers. Now just to show you one more thing here. Let's say I wanted to find my minimum, second kel, and I want to find a minimum, but I define my left bound way over here at negative 2. And I define my right bound over at 1.3. 1.3. Enter. So now you can see that my interval that I'm looking at is from here, but instead of being covering one local minimum, it covers two of them, because it's now way over here, and it's covering both of my local minimums. Well, the calculator doesn't know the word local. It just says, what's the minimum in this interval? And I'm not going to make a guess. And what it's going to give me is the first one, because the first one is the minimum of my minimums. But it completely ignores my second one. So you have to be really careful in defining the interval that you're looking for. And when we talk about interval, we'll talk about intervals of x.